Hello, my name is Gavin Doby, and welcome to my presentation for my Operating Systems course, Project 1, on Multi-Threaded Programming and Interprocess Communication. During this presentation, I will walk you through my project file by file, which embraces the healthcare theme, and I'll use this to demonstrate the fundamental concepts of concurrent programming and interprocess communication. My project was developed in a Linux environment using Ubuntu on the Windows subsystem for Linux, WSL. This project was developed in a Linux environment using Ubuntu on the Windows subsystem for Linux, aka WSL. By leveraging WSL, I was able to integrate a Linux-based workflow while maintaining compatibility with my existing Windows setup. This approach ensures that my project adheres to real-world Linux-based system programming principles while making it easier to scale and as well to apply to enterprise and cloud-based environments. Now I'll explain how each of my implementations not only meets the project requirements given to me, but also reinforces my understanding of multi-threading, interprocess communication, resource protection, etc. Now that I've introduced my project, let's start with Phase 1. This phase introduces the fundamentals of multi-threading. In this file, I create multiple threads, each representing a nurse checking a patient's vital signs. The code spawns 3 threads that execute concurrently without sharing any data. As you can see in the code, each thread prints a message before and after a simulated delay. I'm running this program through the command line using Cargo, which is Rust's package manager and build system. Given that all of my files are properly defined in the cargo.toml file and using the bin syntax, I can now run them through my command line using the cargo run -bin and then whichever phase I would like to run. Now that I've introduced you to my first phase, let's go ahead and run that using the cargo-bin phase 1 command. And as you can see, the program works as expected. It creates 3 threads of nurses checking the patient's vital signs, with each different starting times, and then they finish at 3 different times, as expected. The code I've shown you demonstrates each of their project requirements by creating multiple threads that run concurrently. Each thread represents a nurse checking a patient's vital signs using the thread spawn command. Since no data is shared between the threads, there are no race conditions, and the move keyword I used ensures proper ownership within each thread. The program confirms parallel execution because, without threading, this process would take a total of 6 seconds. However, with threading, all of the nurses finish in simply 2 because they are running at the same time. Now, let us move on to Phase 2, where I introduced resource protection using mutexes. Now onto Phase 2, where I introduce resource protection using mutexes. In this file, multiple threads update a shared patient record. Since multiple nurses need to modify the same data, I use the arc mutex patient record command to ensure safe concurrent access. On one hand, the mutex allows only one nurse at a time to modify the record, preventing data corruption from multiple updates at the same time. The arc, aka atomic reference counter, is necessary because multiple threads need to share ownership of the patient record across thread boundaries. Without arc, Rust would not allow multiple threads to access the same resource safely. This is a Rust-specific feature. Now let's run Phase 2 and see the given outputs. Once again, we're going to run the cargo run -bin and then the phase we want to run. And as we can see, each and every nurse is updating the patient records independently. We see they're increasing by 1, as they should, as each nurse touches it, and they're touching them independently, updating them atomically. This satisfies my project requirements because each nurse locks the patient record and updates the treatment count and releases the lock. This prevents race conditions, ensuring that no two threads modify the record at the same time. The expected output confirms that the treatment count increases consistently without corruption and demonstrating proper synchronization. Now, let us move on to Phase 3, Intentional Deadlock Creation. Our goal here is to intentionally create a deadlock scenario. This phase meets the project requirements by demonstrating how improper locking order can prevent threads from ever making progress. Our code here spawns multiple threads, each that attempt to lock shared resources in an inconsistent order, leading to a circular wait condition. In our code, each nurse tries to first lock the patient record mutex, and then pauses briefly before attempting to lock the surgery mutex. However, since another thread may have already locked surgeries and is waiting to lock patient record, a circular wait can occur, causing the program to freeze indefinitely. This confirms the presence of a deadlock, meeting the requirement of demonstrating unsafe resource management and concurrent execution. Now, let us run Phase 3 and see the expected output, or the lack thereof. Once again, we are going to use the cargo, run, bin, and then our specified phase, and let's see what the output is. As you can see, the program is continually running while providing us no output. This would be due to our inconsistent lock creation. What we have here is a program that has reached a deadlock and will run indefinitely. Now, let us move on to Phase 4, where I will try to resolve this issue by implementing proper lock ordering and creation and introducing a non-blocking try-lock mechanism. Now, in Phase 4, I will resolve the deadlock I tried creating in Phase 3. This phase meets my project requirements by demonstrating proper resource management using properly structured lock ordering and using a non-blocking try-lock mechanism. Instead of threads indefinitely waiting on each other, this implementation ensures that if a thread fails to acquire the second lock, it will reset and release the first lock and try again. This approach eliminates the possibility of circular wait condition, and this approach eliminates the possibility of a circular wait condition and the deadlock that was created in our previous phase. Now, let us run Phase 4 and ensure that proper deadlock prevention is in place. Quickly, I will show you our try lock command that is wrapped in an if statement, so that if a nurse fails to lock the second lock, as we can see here, it'll print nurse could not acquire, retrying, and then it will try to lock it again. Like before, let us use the cargo run bin command, and we can see that all locks were successfully locked and unlocked based on our print statements. Finally, in the second section of my project, I will demonstrate proper inter-process communication using pipes and Rust. This phase meets the project requirements by properly implementing direct process-to-process communication following the producer-consumer model. Here, the doctor process acts as the producer, generating a patient report and writing it to the pipe, while the nurse process is the consumer, which reads and processes the report. This setup mimics real-world hospital scenarios where multiple entities exchange critical data in a synchronized manner. In the code, I use the pipe system to call and create a unidirectional communication channel. The fork system call then creates a separate doctor and separate nurse process. The doctor writes a patient report into the pipe while the nurse reads from it. This ensures that data flows correctly between the processes. In addition, proper error handling is implemented to prevent broken pipes and unexpected process failures. Now, let us run the second section of our project and ensure that proper inter-process communication is achieved and demonstrated. The expected output would be that the nurse successfully receives and reads the report, proving that our IPC mechanism worked correctly. Now, let us run this file using the same command we have before, the cargo run command. And as we can see, the nurse properly received the report and the info of said report. This shows that our inter-process communication worked properly. Not only did our producer correctly send information, but our consumer received and returned that information to us. To conclude, this project has covered the fundamental concepts of multi-threading and inter-process communication in operating systems using Linux and Ubuntu through WSL. Across all phases, I've demonstrated how to create and manage threads, enforce resource protection with mutexes, and also identify and resolve deadlocks, and as well as implement IPC using pipes and Linux. Each phase has showcased real-world challenges and solutions related to concurrency, demonstrating key techniques used in modern multi-threaded solutions. In Phase 1, we explored basic thread operations where multiple nurses worked in parallel without the chance of blocking each other. In Phase 2, we introduced synchronization using mutexes, ensuring safe access to shared data among threads. In Phase 3, we intentionally created a deadlock scenario, illustrating one of the biggest pitfalls in concurrent programming. Finally, Phase 4 showed us how to prevent said deadlock using proper lock ordering and retry mechanisms. Finally, Phase 4 showed us how to prevent said deadlocks using proper lock ordering and retry mechanisms. And in Project B, we demonstrated process-to-process communication using the producer-consumer model using IPC pipes. Overall, this project has greatly deepened my understanding of synchronization, race conditions, inter-process communication, and deadlock prevention, all core principles of operating systems. Mastering these techniques is essential for building reliable, efficient, and scalable software, especially when dealing with multi-threaded and distributed environments. Thank you so much for watching my presentation. I welcome any questions, and this has been Gavin Doby.